Okay. 자, automated RTL update for abutted design. Introduction. The most important factor to be considered for SoC system on chip design are performance, power, and area. Among them, the absolute factor directly related the cost of the chip manufacturer in the area. Therefore, new technologies to reduce chip area are being continuously researched. One of the various technologies to reduce chip area is to design a abutted floor plan. Abutted floor plan can reduce area by eliminating top-level routing area in the chip. For abutted design, RTL register transfer level should be updated for reflecting design modification requested by physical designers, without a human error, in a short time. This paper introduced the RTL update automation methodology for abutted design. Challenges. Due to the huge size of the mobile AP application processor SoC design, the limitation of the EDA, electronic design automation tool capacity, and computing resources. Full chip integration is performed by the divide and conquer. Therefore, SoC full chip design is divided into a lot of function blocks, and the integration of each function block is performed by the block integration engineer. Function block designer is in charge of the creation of the block level RTL, sanity check of the generated RTL like lint, low power design, performance area estimation, and so on. After doing these works, RTL of the function block is released to SoC-top designer to make SoC top RTL for next chip design step, such as physical implementation and function verification. For abutted design, RTL update requests coming from physical designers are to create feed-through, which is a connection to be passing through multiple function blocks and to move function logics of SoC top into multiple function blocks. Hence, RTL modification regarding abutted design should be performed by many block integration engineers simultaneously because it is possible to make SoC top design after all function blocks are developed. Moreover, the RTL modification should be rapidly executed not to cause any delay of chip production because the RTL modifications are occurring to the abutted design requested at the late stage of the chip design, and the amount of RTL that needs modification is huge. Also, if there is a mismatch between the function blocks, as such top design is difficult to complete due to the mismatch. This means that the automation of RTL update for abutted design is inevitable. Metadata-based SoC RTL integration automation. In order to develop RTL design automation flow, there are several ways to modify the value-based RTL design. However, if the amount of the complexity of the design modification is huge, it's very difficult to modify the Verilog RTL codes directly without converting Verilog RTL design into design metadata. A representative metadata technology in the semiconductor industry is IP-XACT. IP-XACT is IEEE standard 1685 as IEEE standards is XML, extensible markup language schema that define and describe the electronic components and their designs. Goal of the Goals of IP-XACT are to enable exchanging of complex component libraries between ED tools and for SoC design, to ensure delivery of the compatible component description from the multiple component vendors, to describing configurable components using metadata, and to enable the provision of the EDA vendor neutral script for component creation and configuration. Also, it's possible to develop various automation methodologies because IP-XACT is machine readable. There are 7 main contents in IP-XACT as bus definition, abstraction definition, component, abstractor, design configuration, and generate chain. In our design flow, bus definition, abstraction definition, component, and design has been used. Bus definition includes a name of the bus such as AXI, AHB, and logical port list, which is composed of the bus definition is described in an abstraction definition. Component includes IP specification information such as port list, bus interface, SFR, special function register, the file list, and so on. In design, instance and connection information are included. In design, instance and connection information are included. The figure 1 shows an example of IP-XACT component. Figure 1, IP-XACT component example. When you are using IP-XACT in integration flow for generating RTL for function block and SoC-top, Figure 2 shows SoC RTL integration flow using IP-XACT. Figure 2, SoC design flow using IP-XACT. The first step of RTL design flow is to make IP-XACT component of IP using IP packaging flow. During IP packaging, a description of the IP port list is performed and added into IP-XACT. Also, bus interfaces are added into IP-XACT by mapping logical ports defined in abstraction definition and physical ports existed in the actual IP. These IP packaging tasks are performed by IP designers. IP-XACT component of all IPs which are used in a SoC project should be delivered for SoC top-level integration because IP-XACT component of IP is a mandatory deliverables for integration. The IP-XACT of several IPs, such as legacy or purchased IP, is made by SoC integration team. After obtaining the IP or IP-XACT components from IP design teams, function blocks would be integrated as IP-XACT design. In IP-XACT design, there are 2 kinds of connections, such as an interface and port. Interfaces are connected through the interface connection between IPs. When the interface connection is performed, logical ports with the same name as the port name defined in the abstraction definition are physically connected. The interface connection covers 50% of the overall connection in terms of a port in a SoC design. Remaining ports are connected through a port connection called an ad hoc connection. In ad hoc connection, there are inter-IP connections and connections to constant values such as 0 and 1. Generally, in a SoC design, there are thousands of interface connections and over 50,000 ad hoc connections. Therefore, automation methodology for ad hoc connection is essential to prevent human errors and to reduce TAT, turnaround time. Most of ad hoc connections are related to system-level IPs. System-level IPs control chip-level operations such as clock and power management, test mode, test box, interruption, and so on. We developed various RTL design automation methodology based on IP-XACT metadata for the system-level IP, such that a design modification like IP instantiations and ad hoc connections. They can be performed by executing the modification script on the metadata-based design platform. A specification of a system-level IP is described in the dedicated editor, and the function block designers describe IP form information related to the system-level IP using the editor. After collecting information of all IPs, system-level IP designers generate RTL over their system-level IP from the specification, and also they make IP connection scripts for the system-level IP integration and function block. The developed RTL codes and connection scripts for system-level IP are delivered to a function block and the SoC-top designers. Then the function block designers execute the connection script for integration of system-level IP. In case of SoC-top design, almost ports are connected by the interface connection between the function blocks, and other connections related with the system-level IPs are performed by the connection script. After completion of SoC-top integration, RTL code for SoC-top design are delivered to the physical and verification engineers. For example, at the previous design flow for the test mux IP integration, function block integration engineers connected all ports manually by referring integration guide documents. As a result, a lot of time was spent for the IP integration and for solving a lot of design issues caused by human errors. However, in current flow, if someone describes test mode specification of SoC design, this specification is automatically converted into several scripts that can be executed for generating test mux RTL codes, instantiating test mux IP and the port connecting between test IP and other IPs, and then each function block design executed the generated script to integrate the test mux into their own function block. At the SoC-top integration using an updated function block, SoC integration can be executed with a generated script. Once all designs are updated with the execution of a script, metadata of a design SoC design would be updated and the RTL code for SoC-top and each function block would be generated from the metadata-based design platform. Due to this automation methodology using IP-XACT as a metadata, it's possible to modify RTL in a very short time without any human errors. Abutted design. Figure 3 shows the overall design flow for abutted design. Figure 3 design flow for abutted design. The first deliverable for the abutted design is the initial RTL code of function blocks and SoC-top with the top-level function logic. Physical implementation engineers synthesize the delivered RTL code and perform the P&R, placement, and route using the synthesized len list. In this step, top-level channel routes are existed for routing of a top-level function logic such as the test mode control IP, the data communication modules between function blocks, and so on. After fixing a location of the function block, the top-level function logics are moved into the agency block function blocks considering the physical timing. If all top-level function logics are relocated into multiple function blocks and the relocated information related with the abutted design is delivered to RTL designer for updating RTL code of all functions of SoC-top. To modify the RTL codes of function blocks and the SoC-top, top-level logic designers generated the connection script to reflect the abutted information to RTL code. These generated connection scripts are automatically executed at the function blocks and the SoC-top designed to modify the RTL codes. The updated RTL codes are delivered to a physical implementation engineers. To make a successful implementation of abutted design in time, automation flow of RTL updating without any error in a short time is essential because this process must be repeated whenever P&R is changed. Furthermore, the P&R can be changed frequently in SoC project. Figure 4 shows RTL updated item. Figure 4 shows various RTL design modification for abutted design. Figure 4 design modification for abutted design. The RTL design modification to do the abutted design are as follows. Test mode control IP movement. In our SoC design, test mode control IP which generated test mode selection signal is located at the top level like IP with blue line in figure 4. Typically, number of test modes in SoC design is the number of the number of test modes in SoC design is around 50 and the number of function blocks is around 30. Therefore, there are many connections between the test mode, controller IP, and the function block. For abutted design, the controller IPs should be moved into a function blocks located in the center of the chip. And this movement leads RTL update of SoC-top and function block design. The data communication between blocks. There is a data communication between function blocks. To exchange data between the function blocks, the data could be communicated through top-level channels. When using the top-level routing channel to when use top-level channel to satisfy the physical timing conditions. Additional logics such as register slices could be added to the SoC-top design. In order to manage register slices at the port group level, we developed the slice register IP, and it is designed to be configurable for setting various timing conditions without design changes. Figure 5. Before-after abutted design connection related data communication. The figure 5 shows RTL code's updated example regarding data communication due to the abutted design. Prior to the abutted design, data between the block A and the block E could be directly connected using the 3 interface connections. And however, after applying the abutted design, 11 interface connections and 2 instances of the register slice module in block B and D are needed for the data communication without timing violation. Also, many parameters should be set in register slice IPs to avoid timing violation. The test signal from pad. For chip test, some I/O pads are directly connected to function blocks. To meet physical timing for test, a module including the flip-flops is added on a path between the pad and the function block. For abutted design, the flip-flops should be moved into function blocks. Unlike the register slice modules for data communication between function blocks, the flip-flops should be respectively separated due to different glue logic related to each flip-flop. Due to the separation of flip-flops, function blocks and the SoC-top design should be updated as a figure 6. Before applying the abutted design, all flip-flops for timing satisfaction exist in a module. After applying abutted design, all flip-flops relocated into functions and many connections should be created at the function blocks and SoC-top. Figure 6. Before and after abutted design connection related to the test signal. The RTL updated automation flow. Figure 7 shows the RTL updated automation flow. Figure 7 RTL updated automation flow. To maximize the efficiency of automation for abutted design, we define the metadata format for RTL modification requests coming from the physical designers using JSON. JSON JavaScript object notation is the right way data interchange format. It is to form humans to read and write. It is easy for machines to parse and generate. JSON is built on 2 structures. A collection of name and value pairs in various languages. This is realized as an object record structure, dictionary, hash table, keyed list, or associative array. An ordered list of values. In most languages, this is realized as an array, vector, list, or sequence. After implementing the abutted design, JSON file with the abutted information should be delivered for RTL update by physical implementation engineer. So in the JSON file, there should be a following items as figure 8a. The abutted key. The abutted key of the JSON file is one of the RTL update items for the abutted design. The RTL update items are test control IP name and data communication IP name for register slice, and an IP name related for a test signals connection from pad. Source. In this section, the source means the start point of a path. Destination. Destination means the end of the path. Path is a block list to path from the source to the destination. The figure 8, the JSON template and the example with the abutted information. As figure A, B is shown. Direct connection between block C and E in figure 4A is changed to path connection through block H to 2 abutted design. The change should be described in JSON file. Then these metadata of the request are processed by our automation solution, resulting in script for modification of both function blocks and SoC-top. All automation solutions were implemented with the Python language, and Python libraries for extracting abutted information from the JSON file and generating integration script with the template engine were used in an automation solution. The generated script for all function blocks are delivered to a function block designer. The scripts are automatically executed at the final step of the function block integration. After completion of a function block integration, the function block RTL codes which are updated with the abutted information are released to the SoC-top designers. The RTL code of the SoC-top design is created by executing the connection script at the top level and delivered to a physical and verification engineers for chip implementation and verification. Also to apply to the all updated automation solutions in multiple function blocks at the same time, the version of all function blocks should be matched. For version matching, all connections for abutted design are tagged with a unique version when the connection scripts are executed. The version mismatch could be prevented by checking the version whenever RTL code of a function block are delivered for SoC-top integration. The figure 9, version tag on connection. Result. As the proposed automation solution was applied, value RTL codes were modified for abutted design. Table 1 shows the comparison result of a number of port connections before after the application of automation solution. Table 1, number of connections between before and after abutted design. The number of port connections related to the test mode control IP became a double. The port connection for data communication between the blocks and the port connections to transmit test signals from a pad are increased by the 7.3 times and 6.9 times, respectively. For data communication connection, the multi interfaces are used, and the bus interfaces connection covered 80 port connections. Even though the number of port connections is increased by at least 2 and 7 times, they all new port connections are automatically created for abutted design within a thousand of seconds. Finally, RTL code for function blocks and SoC-top could be created without error. In terms of verification, function verification of SoC design is performed at RTL level without abutted information because there is no functional change to the abutted design, and the abutted information is delivered after the completion of the physical implementation. After verifying the RTL codes without abutted information, a functional consistency between the original RTL codes and abutted design RTL codes in terms of connection is checked by the equivalence checking technology. The conclusion: in this paper, RTL automatic updating solution is proposed. To reduce the area SoC, on abutted design is required, but a large amount of the RTL code modification is required. Moreover, since it is necessary to apply the abutted design very frequently in the late design stage. It's difficult to apply the abutted design as a manual method. In order to prevent human error and to reduce development time, this solution is proposed and developed, and the effect of the verified by applying the actual mobile SoC project. As shown above, the number of port connections increased significantly, so RTL code changes in the function blocks and SoC-top should be made significantly. But the RTL changes should be made without any human error due to the proposed solution. Therefore, RTL can be modified without increasing TAT for abutted design. The reference here is that. Thank you for your time. I read with you is the paper Automated RTL Update for Abutted Design was published in the DVCon, the Design and Verification Conference. Thank you.